What are the trade-offs in amplifier design for power efficiency? Imagine trying to get the most out of your amplifier while using the least amount of energy. That's what power efficiency in amplifier design is all about. But making an amplifier more efficient isn't as simple as flipping a switch. It involves balancing several factors that often work against each other. When you aim to save power, you might find that other parts of the amplifier suffer. For example, reducing power consumption usually means narrowing the bandwidth, which limits the range of frequencies the amplifier can handle well. This is because higher bandwidth requires more bias current and larger transconductance, both of which consume more power. So, if you want a wider frequency response, you might have to accept higher power use. Next, think about gain and stability. An amplifier with high gain can make signals much stronger, but it can also become unstable and start oscillating or producing distortion. To keep it stable, designers often add compensation components or limit gain, which can lower overall efficiency. This means that sometimes, to prevent unwanted behavior, you have to sacrifice some power savings. Noise performance is another tricky area. Reducing noise in an amplifier often demands higher bias currents and more complex circuitry, which increases power use. If you want a low-noise amplifier, you might need to accept higher power consumption, especially in sensitive applications like audio or measurement systems. Distortion is also a key factor. To keep the output clean and linear, the amplifier needs to operate in a linear region with enough bias current. This increases power use. On the other hand, switching amplifiers like Class D or Class T are designed to be more efficient by turning on and off rapidly, but they can introduce more distortion and need filtering to clean up the signal. When it comes to load driving, the type of load matters. Driving capacitive loads at high frequencies makes the amplifier work harder, which reduces efficiency because it has to supply extra current to charge and discharge load capacitances. Larger or more complex loads can make it even harder for low-power amplifiers to perform well. Different amplifier classes also have their own trade-offs. Class A amplifiers are very linear and produce little distortion, but they are very inefficient, often wasting most of the power as heat. Class B and AB are more efficient but can introduce crossover distortion. Class D and T use switching techniques to reach high efficiency, sometimes over 90%, but they requiring careful design to manage electromagnetic interference and distortion. In real-world applications, these trade-offs become even clearer. For battery-powered devices, saving power is essential, so they might accept limited bandwidth or slightly higher noise. High-fidelity audio systems prioritize low distortion and noise, even if that means using more power. Radio frequency amplifiers in communication systems need to balance bandwidth and efficiency to keep signals clear over wide frequency ranges. And in sensor or measurement systems, stability and low noise often take precedence over power savings. So, when designing an amplifier for power efficiency, engineers have to weigh all these factors carefully. Improving one aspect often means compromising another. The goal is to choose the right architecture and operating points that best fit the specific needs of the application, knowing that no single design can excel in every area at once.